Hello everyone, I'm so glad that you chose to join us once again. Today we are going to be consolidating all your knowledge, and what that means is we're going to be practicing all your knowledge on functions and inverses. So we're going to start off by having a look at the quadratic function, or the parabola if you prefer to call it that. Let's have a look at the first question. So we are given that g of x is equal to minus 2x squared. And the first question is state the domain and range. All right, so if we think about, and I always like to make a sketch even though we don't need it. If we think about the function g of x is equal to negative 2x squared, it's going to look something like this. And we can see that the range is going to be all the y values that are less than equal to 0. And the range, the domain is x is an element of real numbers. There's no restriction on x. So therefore, for part A, the domain x is an element of real numbers, and the range is y is less than equal to 0. All right. Now they ask you, how must the domain be restricted so that g is invertible? Now remember, we spoke about a function being invertible before. And what it means is if a function is invertible, that means that the inverse graph is also a function. For the inverse graph to be a function in the case of a parabola, we have to restrict the domain. Okay, so how are we going to restrict the domain so that g is now going to become a function? Well, if we were to draw the inverse graph here, let's just make a quick sketch. It's going to look something like this. Okay. So that would be something like what the graph of the inverse is going to look like. Now for me to restrict the original function, I would either need to restrict to this arm where x is less than equal to 0, or I'll have to restrict to this arm where x is greater than equal to 0. By restricting that function, I will then get one single arm on the inverse graph. So how must the domain be restricted? Well, it can either be restricted to x is less than equal to 0, or we can restrict it by saying x is greater than equal to 0. And that will then produce a graph of the inverse, which will be a function. All right. The next part of it, says find the inverse graph g inverse of x. So we've got g of x, which we'll write as y, is equal to negative 2x squared. To find the inverse, I swap the x and the y values, so I will get x is equal to negative 2y squared. The next step is to solve for y. So I divide both sides of the equation by minus 2, so I get negative x over 2 is equal to y squared. And then I take the square root on both sides, so y is equal to plus or minus the square root of negative x over 2. Remember, at this point, you cannot say this is the inverse function, because at this point, the inverse is not a function as yet. It's only when we restrict the domain that we can start using functional notation. Function notation being the f of x, g of x, h of x, and all of that. We can only use that notation on functions. That makes sense, right? Okay, so how do I restrict it? We said it's either going to be the positive arm or the negative arm. So the functions here would either be f inverse of x is equal to the positive square root of negative x over 2, or the other option would be f inverse of x is equal to negative square root of negative x over 2. Okay, but they didn't ask us to go that far. They just said find the inverse. And in fact, it was supposed to be g, and that's just me not paying attention. So this should be g inverse of x, g inverse of x. All right. State the domain and range of g inverse of x. Now, this all depends on how you restricted your domain, right? So if you're restricted to x is less than equal to 0, then what's going to happen in your inverse? It's going to become the range that's going to be less than equal to 0. So if we restricted the domain in the original function x is less than or equal to 0, then that means the range in the inverse would be y is less than or equal to 0. If we said let's restrict the function g of x, and I keep saying f, apologies, but if we restricted g of x to x being greater than or equal to 0, then it is the range of the inverse that will be greater than or equal to 0. So it depends on how you restricted the original function. So if we said x is less than or equal to 0, then our range is going to become y is less than or equal to 0. If we said x is greater than or equal to 0, then our range is going to be y is greater than or equal to 0. Okay, and then the domain becomes the range, and the range becomes. So if we look at the domain of our original function g of x, our domain here was x as an element of real numbers, right? So then the y values would be y as an element of real numbers in the inverse, but because we restrict it, it's either going to be the negative arm or the positive arm, and it will then be x that is an element of real numbers as the domain of the inverse function g of x. Right, then they say sketch the graphs of g of x and g inverse of x on the same axes. We're going to sketch them. Okay, so if we restrict it to x is less than or equal to 0, which you can see here, so we've got all the negative values of x, we've restricted our domain to. All right, and remember the function g of x, the original function, was all the y values were less than or equal to 0. So now obviously the domain of your inverse function will be x is less than or equal to 0. All right, let's just in fact clear that up because I think I may have confused some of you there. So we said that the range of the original function was y is less than or equal to 0. Okay, so therefore the domain of the inverse, which is not necessarily a function at this stage, the domain became all the x values that were less than or equal to 0. But once we restricted either to the positive or the negative values of x, we then got a graph where we saw that either y was greater than or equal to 0 or y was less than or equal to 0. So it took on the values that x did in the original function. All right, hopefully that clears it up for you if you were misunderstanding a little bit there. All right, so if we now sketch this, so if I use the values where x is less than or equal to 0, so I'm looking at this left-hand side of the function g of x, right? Then the inverse function would be all the y values having values that are negative, so lying below the x-axis. And if you look at your inverse function here, which we're going to call g, all right? Think about if you're putting x values inside a square root there. They have to be negative, guys. Why do they have to be negative? Well, because you cannot take the square root of a negative number. So therefore, in order for the number inside that square root to be positive, x itself has to be negative. So look at what you've got inside that square root. You've got negative x over 2. In order for this to be a value that is positive, x has to be a negative value because negative times negative is a positive, and then I can take the square root. If x was going over onto the positive values, we would get a function that is undefined. Okay, so that in that way it also makes sense that the domain now becomes x is less than or equal to 0. All right. And let's have a look. If we restrict it to the positive arm of the original function g of x, all right, we see that our inverse function, g inverse of x, is now going to be all the positive y values. So all of those values there that lie above the x values, above the x-axis. So therefore the x values, once again, you can see x is on the left-hand side of the y-axis. So all the x values that we're going to substitute in place of x inside the square root are going to be negative, which means this function is going to be defined, okay? So if we restrict the original function to the positive x values, right, then we get an inverse graph, which is also a function. How can we tell that? We use the vertical line test, and we see that this inverse is also a function. And then the range becomes the domain becomes the range. So therefore, if x is greater than or equal to 0 originally, then my domain becomes my range, right? So now the range is going to be y is greater than or equal to 0. And certainly you can see it in your diagram. Here, we said originally x was all the positive values. And now look at y. Y is all the positive values because this graph lies above the x-axis. Okay. All right, guys. And then we can also see, if we're talking about domain and range, you can see that your y values initially were all the values less than or equal to 0. And now in our inverse function, we can see that all the x values are less than or equal to 0 because they lie to the left of the y-axis. Okay, hopefully that cleared up any confusion you had about how to restrict the domain of a parabola in order to get a graph of the inverse being a function as well. All right, so just remember that when we are dealing with parabolas, we can get inverse graphs, yes, but those inverses are not functions. They only become functions when you restrict the domain of the original graph. All right. Okay, guys, with that, I think it is time for us to take a quick break. We're back after this. Hello everyone, welcome back. So today we are looking at some of the practice questions that you would have done and maybe found some problems here and there. So we're continuing with functions and inverses, and we're going to look at question 2, which is on a very important section in grade 12, which is the inverse function of the exponential graph, which is of course the log graph. Let's have a look at the question. So here we are told that the graph shows an exponential function, g of x is equal to a to the power of x, and a is positive, greater than 0. It passes through the point capital A, minus 1 and 3. So the x value is minus 1 and the y value is 3. Now, when we look at this graph, you should start realizing things about the graph and do a little self-check as you go through the question. I can see that this is a decreasing function. How do I know that? Well, as the x values increase, the y values get smaller. So therefore, this is a decreasing function. That tells me that the base here of the exponent must be a fraction between 1 and 0. Okay, so we know and we keep that in mind as we go through the questions. All right, remember when you've got an exponential function, the x-axis, which is the line y is equal to 0, is an asymptote to the graph, which means even though on your screen it looks like the graph is touching the x-axis, if you could really zoom in and zoom in and zoom in, you will see that it doesn't quite reach the x-axis. The x-axis is an asymptote. The line y is equal to 0 is an asymptote, so therefore the graph looks like it's going to touch it, but it never really touches it. So the graph will never have a y value equal to 0. All right, so let's have a look at the first question. Determine the equation of the function g of x. Now to do that, we will of course need to find the value of a. They told us that the point on the graph is given as a is coordinates, x coordinate minus 1, y is 3. So to find the value of little a, all I'm simply going to do is substitute in y is equal to a to the power of x. I'm going to substitute y as 3 and x as negative 1, and then I need to solve for a. Now remember, a very important section throughout your years of school is exponents. It comes up in many, many topics as you go through high school, and certainly if you carry on to study maths further, you will see exponents again. So you need to remember your laws of exponents. A to the power negative 1 is the same as saying 1 over positive a. So in other words, I can rewrite that negative exponent as a positive exponent by changing from where this is in the numerator, this a to the minus 1, by changing its position to the denominator. So a to the minus 1 is 1 over a, so I have 1 over a is equal to 3. So therefore, by cross multiplying and dividing through, I'll get that 1 is equal to 3 times a, so therefore a will be equal to a third. That's one way to do it. Another way that you could do this is you could raise both sides of your equation to the power -1, and you will end up with the same thing. However you manage to get that equation out, you will end up with y is equal to base a third to the power of x. And remember, we said that a needs to be a fraction, and in fact it has turned out to be a fraction, so we know that we are on the right track. Next question is to find the inverse of g. Now remember, all we do to find an inverse is we swap the x and the y values. So here we've got y is equal to a third to the power of x. So we swap x and y, and then we solve for y. So y is an exponent here, and the only way I can get to y is to now change to log form. Remember, a log is just another way to write an exponent, so I rewrite the exponent y as log of the number x to base a third. So you can see the base of your exponent becomes the base of the log as well. Because we are dealing with a function that is invertible, now remember, invertible means that the inverse of the graph is also going to be a function. It means that we can use functional notation. So I can in fact say g inverse of x is equal to log x base a third. All right. Is the inverse of g a function? I've already said yes, it is a function. How do we know? Because the original graph, which was your exponential graph, is a one-to-one function. And a one-to-one function, we did this when we summarized this whole concept. We said a one-to-one function is invertible. And what that means is that its inverse is going to be a function as well. But if you didn't want to do it that way, you could draw the graph and do a vertical line test and prove to yourself that way that the graph will be a function. All right, next question, they say give the coordinates of the point B on the inverse of G and symmetrical to A. So what we've been saying over and over again, x becomes y becomes x, domain becomes range, range becomes domain. That's the idea that we're going to use here. All right. So they're saying find the point on the inverse graph, which we haven't drawn, and it doesn't matter. All we need to remember is that the line y is equal to x will be your axis of symmetry. And all that happens along this line is it produces a graph that's an inverse, and all that happens is your x values become your y values become x values. So I'm going to get a point on the function which I haven't drawn, but the point B is going to be x value 3, y value, in fact it should be below the axis, so ignore that, x value 3, y value -1. All right, so we've swapped the x and the y values around. They then say, is the inverse of g increasing or decreasing? Now, the idea of an increasing and decreasing graph all depends on the value of the base, all right, the base of the exponent or the base of the log graph. Now, when you think about the base of the original function g of x, we said that the value there was a is equal to a third. And I've already mentioned to you that when you get a base that is a fraction in your exponential graph, then you will create a decreasing function. If your original function is a decreasing function, then the inverse graph of the exponential function is going to be a decreasing function as well, because they share the same base. So therefore, the log graph will be a decreasing function as well. Okay, so as you see, we've got an exponential function that's decreasing. We in fact will get a log function that will also be decreasing. All right. So is the inverse increasing or decreasing? It is in fact decreasing because the original function was decreasing. So it makes sense that the inverse graph is also going to be decreasing. Now if we were to go further with this, and they didn't ask for this, but if we go back to our question, let's call it up here. All right, we went a little bit far away from it. There we go. They could have asked you to sketch this graph, and in fact they've given you enough information for you to be able to accurately sketch this graph. Firstly, we know that the log graph is going to be a decreasing function, so I already know the tendency, the shape, right? It's going to be as the x values increase, the y values decrease. But we also know that in inverses, the intercepts swap around. So I know that the x-intercept of the log graph is going to become what the y-intercept of the original function g was. So my x-intercept, since the y-intercept was 0 and 1 on g of x, the x-intercept is going to be the point 1 and 0. We swap the x and the y values around. And then remember we had this point A, which was minus 1, 3. And we said that there's going to be another point here called B, which is going to be on the log graph, on the inverse graph. So therefore I've got 2 points here, and I know that the y-axis is now going to become an asymptote to the log graph. How do I know this? Because we keep repeating the same thing over and over again. We swap around. Remember, in the original function, in the exponential function, it's your x-axis that's an asymptote. So therefore, in my log graph, it's the y-axis that's going to become an asymptote. So you cannot have x equal to 0. So therefore, I know that the y-axis is going to be acting as an asymptote. So therefore, we can draw this inverse graph if they asked us for it, which they didn't in this case, but we can draw g inverse of x using the information that we have already found. So we've got the x-intercept, we've got a point on the graph, x is 3, y is minus 1. We've got the shape of the graph, and we know that the y-axis will be an asymptote. So therefore, it is quite simple to then draw the decreasing log graph, which would be the inverse of the original graph. All right, guys, so that question is then easy for us to unpack because we understand how an inverse graph is affected by this line of symmetry, this line y is equal to x, okay? So some of the important things that we've done with the questions today is we've looked at how the domain becomes the range becomes the domain, and also we've looked at, now when we look at exponential and log graphs, we've looked at how the asymptotes change around. So initially it was the x-axis that is an asymptote to the exponential graph, and then when we look at the log graph, it is the y-axis that becomes an asymptote to that function. Thank you so much for joining us today. That is all that we have time for, and we'll see you again next time. Cheers.